In this video, we are going to study about what are operators, what is the position operator, what is the linear momentum operator, and the total energy Hamiltonian operator. First of all, what is an operator? These are some symbols that are familiar to us. If we see a plus sign and we see two quantities on either side of the plus sign, we know that we have to add them together to get the result. In this case, 11. If we see a minus sign, then we know that we have to subtract the quantity on the right of the minus sign from the quantity on the left of the minus sign to get the result. Similarly, if we see the percentage sign, we know that we have to take the percentage. Now let us look at the operators that we encounter in quantum. First is the position operator. The position operator is denoted by the symbol x cap, and it's simply a multiplication. Momentum operator is given by p cap of x, and that is minus I h cross d by dx. This is the linear momentum operator in the x-axis. So if we have the x, y, and z axis, then we have the linear momentum along the y-axis as minus I h cross d by dy, and the linear momentum along the z-axis as minus I h cross d by dz, where h cross equals h over 2 pi and h is Planck's constant. So the total linear momentum would be the sum of the linear momentums in the x-axis, y-axis, and z-axis. So total linear momentum would be p cap of x plus p cap of y plus p cap of z, and that is minus I h cross dou by dou x plus minus I h cross dou by dou y plus minus I h cross dou by dou z, which would be minus I h cross dou by dou x plus dou by dou y plus dou by dou z. This is the total linear momentum operator. Coming to energy. Energy is kinetic energy plus potential energy. Potential energy is denoted as V cap of x when it is in the x-axis. So total potential energy is the potential energy in the x-axis plus the potential energy in the y-axis plus potential energy in the z-axis. Coming to kinetic energy, we know that kinetic energy is half mv squared, where m is the mass and v is the speed. Multiplying the numerator and denominator by m, we get half m squared v squared over m. M times v is the momentum, which is p, the linear momentum p that we saw before. So we can write kinetic energy as half p squared over m. So we can now apply the linear momentum operator p squared, p cap squared. So the kinetic energy operator would be 1 by 2m p cap squared, which is 1 by 2m minus ih cross dou by dou x plus dou by dou y plus dou by dou z, the whole square, which is 1 by 2m times I squared equals negative 1. So we get minus 1 by 2m times h cross squared times dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared. This is the second derivative. Which means you take the derivative of the function and then you take the derivative of the result of the first derivative. Dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared is denoted as del squared. So kinetic energy operator is minus h cross squared by 2m del squared. Hamiltonian is the total energy, so it's a sum of potential energy plus kinetic energy, and it is this sum of the total energy in all three directions, h-axis, y-axis and z-axis. So that will give us v cap of x plus v cap of y plus v cap of z, which is the potential energy, plus minus h cross squared by 2m del squared. That would be the Hamiltonian operator. What is the linear momentum of a free particle described by the wave functions xi of x equals e to the power ikx and xi of x equals e to the power minus ikx? So we saw from the definition of the operator for linear momentum P of x is minus ih cross dou by dou x. So operating this on the function xi of x, we get minus ih cross dou by dou x of e to the power ikx. Derivative of e to the power, say mx, equals m e to the power mx. So applying this, we get minus IH cross IK times e to the power IKX. I squared equals -1. Plugging this value, we get negative of I squared h cross k e to the power ikx. I squared is -1, so negative of -1 is positive, so we get h cross k e to the power ikx. This can also be written as h cross k xi. So operating the linear momentum operator on xi gives us h cross k xi. Part B, xi of x equals e to the power minus I kx. Again, linear momentum operator is minus IH cross dou by dou x of xi of x, which is minus IH cross dou by dou x of e to the power minus ikx. Since dou by dou x of e to the power mx equals m e to the power mx, we can say this is minus IH cross minus ik times e to the power minus ikx. Which is equal to I squared equals -1 h cross k e to the power minus ikx. This can be written as minus h cross k xi. So operating the linear momentum on xi gives us minus h cross xi. Construct the potential energy operator of a particle with potential energy V of x equals half kf x squared, where kf is a constant. To construct the potential energy operator, we can replace the position x by the operator x. So V cap of x, which is the potential energy operator, would be half of kf times x cap squared, where x cap is a position operator. We know that the position operator x cap is multiplication by x. Which means x cap is equal to x times. So the potential energy operator V cap of x is simply half kf x squared.